Γεια σας, είμαι ο Φώτης Κουτρούλης και αυτό είναι το ερευνητικό σεμινάριο για τη θέση του επίκουρου καθηγητή στην ΣΕΜΦΕ. So for the next 30 minutes, approximately 30 minutes, let me switch to English and present my work. So in this talk, I will talk about cosmological gravitational particle production as dark matter origin. Of course, I will focus on sterile neutrinos in this specific case. However, this framework is general and you can produce any particle, any kind of dark matter particle, but let me focus on sterile neutrinos. On top of that, I will not give much attention on the fin of sterile neutrinos as dark matter, which is more or less known and has some shifts, of course, in this framework, but it's not the part of this work. I will mostly focus on the production of that particles and the possibility to be a viable candidate. So this work is based on these two works here. One is already published in JHEP in collaboration with Oleg Lebedev and Stefan Pokorsky, and the other is already accepted for publication at JCAP in collaboration with Duarte da Silva, Oleg Lebedev, and Stefan Pokorsky. So let me start by giving you a small introduction and motivation about what I'm doing and why I'm doing that. And then I will show you how you can produce sterile neutrinos given this cosmological gravitational particle production during inflation and then after inflation. Two different mechanisms, but also interrelated. And after that, showing you that this could be a viable candidate and under which condition can be a viable candidate for a dark matter particle, I will finish with my conclusion. So, first of all, I don't need to convince anybody that dark matter exists. Of course, we know that it exists because we have a lot of compelling evidences for its existence, and actually, these evidences come also on many different, very different astrophysical scales. Like we have information from galactic calculation about the speed of the rotation of the galaxy, the stability of their existence. We have information about the cluster of galaxies, how they move, combine, and how they do not spread away because of the existence of dark matter. And of course, we have information from CMB and other cosmological observations about its existence. So dark matter exists. And on top of that, we know that it corresponds to approximately 84% of the matter in the universe. So most of the matter in the universe is dark. According to these measurements, we also know that the dark matter candidate should be stable, at least compared to the lifetime of the universe. It is mostly or dominantly non-relativistic, it's called, and it is electrically neutral and colorless. So it seems that there are only gravitational interactions that matter or take into account for dark matter observations, and every other interaction is either negligible or not existing at all. So we know that dark matter exists. We can calculate many things about its presence in the universe, but we don't know what it is and how it is produced. Because of that, there is a big dark matter zoology. As you can see here, there is a big tree where the main part is dark matter, and there are several branches and sub-branches that they can describe a possibility about how dark matter originated and what is dark matter, and this spans a big scale, a big difference about models, like coming from hexadimensional models, from ultralight dark matter, or for macroscopic candidates, and because of that, also dark matter possible candidates span a huge range of masses from 10 to minus 22 eV, the ultralight dark matter scenarios, to few solar masses, which is like primordial black holes. So also, this gives us two problems. One, because we have a huge amount of possibilities about dark matter candidacy, and the second one is that there is no a huge sharpness of the experiments around which mass scale they look for. This mass scale span 80 orders of magnitude. So in this talk, I will not give a huge breakthrough, adding a new branch to that tree, which in order actually could be the solution, but I will take advantage of something which is essentially based on gravitational or purely gravitational interaction, and this is gravitationally produced sterile neutrinos as non-thermal dark matter. So I will use sterile neutrinos that are already existing within a framework that it is kind of novel. So my focus and this framework says that dark matter is produced cosmologically, purely gravitationally, and there are no other interaction with the standard model. So in order to continue in that direction, let me give you some introduction about what we look for in order to see if this dark matter candidate or this dark matter production mechanism is enough or not. And this information here will have an overlap between the inflationary production of dark matter and post-inflationary production of dark matter. So we start, since we focus on sterile neutrinos, as I said, this mechanism could be generalized, but now we'll focus on sterile neutrinos. We start with the conformal invariant fermionic action of a field of a fermion psi with mass m. This is a breaking scale. Actually, this is the reason that the scale invariance is broken. And we start on an FRW conformally flat metric. As you can see here is the metric. This is the action here, which corresponds to this fermionic dark matter and gives you the equation of motion, as you can see here. Now performing a Weyl transformation on the metric and rescaling the fermions and the field branes and moving to conformal time, actually denoted by eta here. This equation of motion, which is very important for what we are calculating, is transformed to this relation here and tells us that this conformally invariant fermion action on this conformally flat metric is equivalent to a equation of motion of a fermion on a flat space-time, but with time-dependent mass. So flat space Dirac equation with time-dependent mass causes particle production. This is well known many years, already 50 years now. So now that we have this information, the only thing left essentially, which is the non-trivial part, is to solve the equation of motion and to see how this particle production effect comes to the game. So what is the basics of the model in order to do that? Most of this information will be relevant for the during inflation production, but some of them are overlapping with post-inflationary production, as I said. So we have the fermion field, we break it into ladder operators and modes. Then we rewrite the modes in this form, assuming especially homogeneity. So the only non-trivial information comes in the mode functions as a function of the conformal time, and we have the helicity. We do the same for the U modes and the V modes. And now we can rotate this in order to connect these modes at a given time to any other mode given to any other time. So which would be a step that I will describe momentarily. But the main point here is that these modes, they should respect the specific commutation relation here, and also we have the helicity normalization as it can be given here. Based on this information, at a given choice of time or at a given moment, we can rewrite the equation of motion as it is rewritten here. So you can see that we have the small u's, UA and UB, which is only time dependent, and this is the equation of motion, and they, because they are fermions, should respect this mode function should respect this constraint here, which comes from the Pauli exclusion principle. Now it's time to choose a vacuum. Now we choose a vacuum such that we choose the Barnes-Davis vacuum, such that the A and the B, all that vacuum gives you 0, the ladder operators, and then we choose two boundary conditions. At minus infinity of conformal time, we have flat Minkowski space, as you can see here, and the same information is given also for approximately for the out observer, which is at plus infinity of conformal time. So now, having these two boundary conditions and having two observers, the in and the out, we can connect these two by a rotation, as I said previously, and as it's given here on the mode function level. This will give us the Bogoliubov coefficient, beta Ks, and from that we can calculate the particle production, the number of particle production, which is essentially is the beta K squared of the out observer given on the in vacuum. This is a standard procedure. And from that, we can calculate the average number density of these cosmologically gravitationally produced particles. Keep in mind that since this Bogoliubov coefficient is time independent, when we do two calculations, we will calculate everything around the eta E, which is the time of the end of inflation, and approximately will be 0. We have this freedom to do it. Let me just pause for a moment to say that there were other works that they care about fermionic particle production, but not in the concept of sterile neutrinos, and not also in the concept of dark matter particle production, neither sterile neutrinos as dark matter particles. Plus, there is a huge business, recent also business about gravitational production of particles, but this is due graviton exchange here, and it is after the end of inflation. That's why our work is distinguished from this previous literature. So now, since we have all the information or most of the information that we need in order to proceed, I can separate the particle production into scenarios. First of all is inflationary production. In inflationary production, we have the following. Even though we talk about particle production during inflation, in order to see the effect as the out observer, we need to specify the end after the end of inflation characteristics. For that, we focus on radiation-dominated universe. We have calculated also for matter domination, but see the results are not much different here. So we choose the scale factor to be parameterized by these equations here, which connects the end of inflation with a radiation-dominated universe. Then we assume three right-handed Dirac neutrinos. Two of them are responsible for the neutrino masses, like a seesaw mechanism, usually type 1, and the lightest would be the dark matter candidate. So now, for a time-dependent fermion mass, given generally like this relation, the equation of motion that I showed you previously in this matrix formation is broken into two parts, given by these two equations here for the UA mode and the UB mode. And before we move on to solve this equation of motion, it's one thing that is very important to take into account and usually is missed in the literature, and the fact that scalar fields like the Higgs, minimally coupled to gravity, admit a random walk in the early universe, which means that for different Hubble patches, these fields admit a different vacuum expectation value due to this random walk, which is called Sarobinsky-Yokoyama approach, and tells us that in different Hubble patches of the universe, this scalar field, the Higgs in this case, will admit different vacuum expectation values. So in this case, for example, we have the Higgs to be proportional to the Hubble at the end of inflation. This means that the Higgs admits a very high VEV. And if this is true, then the non-trivial, non-zero Yukawa coupling between the Dirac sterile neutrinos and the Higgs, it will give an extra information of time-dependent mass, which is given by this middle term here. So the time-dependent mass is a Yukawa interaction plus a small m. This is very crucial in order to see how big would be the effect of this gravitationally produced sterile neutrinos. And I will show you why. So the setup here to keep in mind is that we have the Hubble approximately constant during inflation, and at some point at AE, when the A is a scale factor, the inflation ends and the Hubble starts decreasing. So this has an effect on the mass of the sterile neutrinos, or the mass that I showed you previously, that they remain constant and in a high scale due to the Yukawa coupling and the Higgs condensate until not AE but A0, another time after AE, after the end of inflation, where the condensate decays. So now there are two scenarios. Either this condensate decays instantaneously, so we have a kind of step function mass difference. You go from the blue line here directly down to the blue line here, or it is smoothly decreased because the sterile neutrinos are produced during a thermal bath, which is already existing because of the oscillation of the inflaton. So they admit the thermal mass, and this smooths the whole procedure. We have checked both scenarios, but however, here we will focus on the step function. I will present the step function mass. On top of that, there are three mechanisms for sterile neutrino production in this scenario. One is the gravitational production that I'm talking about, and the other is the Higgs condensate decay itself and the standard freezing mechanism. We calculated all of them. I will focus on the first, but at the end I will show you a comparison. So given everything that I described, we have the step function mass. So the step function is parameterized like this with step functions, and the two masses in the different time regimes is given by this. So we have to calculate the in-wave function, or the in-mode function solution. And we do that for UA and UB, just changing from capital M to minus capital M with the standard boundary conditions. This gives us the known result, the Hankel parameters, And for scales that are smaller than the scale at the end of inflation, we have this approximate equation which will be helpful for analytic calculations. Now we do the same for the out case. We have two regimes. One is for eta bigger than eta 0 after the decay of the condensate, and another one which is eta between the end of inflation and the time that the condensate decays. And the only difference is just the first case has only the small mass because there is no condensate, and the other case is to replace the small mass with big mass because condensate is there. This will give us this set of out mode function solutions, and again for small enough modes we get these approximately mode functions at the end of inflation because everything is calculated at the end of inflation. So what we have done up to now, we have calculated the in mode functions, we have calculated the out mode functions in two different regimes, time regimes, and now we can put everything together, suing the boundary condition essentially, to the Bogoliubov coefficient. So the Bogoliubov coefficient in this scenario is given by this equation here, which connects the in and out mode functions, and given the mode regimes that I told you previously, the Bogoliubov coefficient analytically is given by this result here. Of course, we have done both a numerical and analytical calculation, and the analytical is here and the numerical is in this plot. I will explain momentarily. And what we find is that there are two cutoffs. One cutoff is related to the case that you have only the small mass, no condensate, and the other cutoff is related to the case that you have both the condensate and the small mass. So as you can see in this plot, we compare the blue line, which is the case that you have only the small mass, no condensate, with the case gray line, which has the condensate on. So as you can see, the blue line drops. There is a particle production initially for a very small mode range, and then drops very, very, very fastly without producing enough particles. On the other hand, for the case of the Higgs condensate on, you have two plateaus, one initially around 0.5 of Bogoliubov coefficient and another one around 0.05. And as you can see, the cutoff after which the Bogoliubov coefficient becomes really insufficient is this case star. It's much, much later. So you have bigger production of particles and bigger modes of particles that are produced. And this is a non-relativistic particle production, since this cutoff here tells us that the Hubble parameter at the scale that the Hubble equals the mass corresponds to k star tilde equals am times the mass. So you can see that the co-moving three momenta that they are produced up to that cutoff, after which the particle production goes really down, are smaller than the mass of the modes produced, of the particle produced, which means they are non-relativistic. So indeed, we produce in that scenario sterile neutrinos, a big number of sterile neutrinos, which is non-relativistic. However, the question is if and when this particle production is enough. So in order to do that, we calculate, as I said, the number density, which is given by this relation here. And as you can see, it will be proportional to the distance between end of inflation and decay of the condensate, and strongly depends on the mass of the sterile neutrinos. So we calculate the Rayleigh abundance in the standard way using these relations here, and we found out in the step function this Rayleigh abundance, and now we can compare with the dark matter Rayleigh abundance constraints, observational constraints. And what we find is that in order for this production, even though we have a big mass for the sterile neutrinos due to the condensate, we found that in order for this particle production to be enough, we need to have a very, really heavy sterile neutrinos. Otherwise, this production mechanism is insufficient, or if you have a very, very small Yukawa coupling. And on top of that, we have calculated and compared with this Rayleigh abundance, the Rayleigh abundance of sterile neutrinos coming directly from the Higgs condensate and from the standard freezing mechanism, and we find that both are much, much bigger, which means at the end of the day that that this production mechanism matters only for a very heavy sterile neutrino production. And why this is bad in this case and not enough? Because for these heavy masses, we are already within a regime, as you can see here, where either these neutrinos the lifetime of the neutrino is much smaller than the age of the universe, or you can reach easily the overproduction bound. So it is completely constrained and excluded from the experiment. So ideally, we would like to be on the left up part here. And we will see that this is the case for post-inflationary particle production. So in this scenario, we have that after the end of inflation, the inflaton field oscillates around its minimum. Again, we have a classical time-dependent background, which naturally produces particles. Now, quantum and classical, of course, gravity effects induce gauge-invariant Planck-suppressed operators among various fields, including the inflaton. And we have particle production, which takes place even in the absence of direct renormalizable couplings between inflaton and other fields. So for a value of the inflaton field at the end of the inflation smaller than m Planck, we can use an inflation EFT description, and we end up with the dimension 5 operator with the Wilson coefficient. As you can see here, the Wilson coefficient is C, this phi square psi bar psi, where we have assumed some Z2 symmetry and parity conservation, just to make our life easier. These extra operators that are forbidden, they will not affect drastically or almost at all the discussion. So we have this 5-dimensional operator. And before we move on, let me comment on this Wilson coefficient. First of all, in order to completely know this Wilson coefficient, demands a complete quantum gravity theory, for example, via an n-point function in string theory, as people have shown here. So we don't have any information coming from that because we don't handle quantum gravity. In addition, we have a different structure compared to those generated by graviton exchange, as the literature that I showed you previously, and such that there is no relation between this Wilson coefficient and the stress tensor. And finally, this dimension 5 operator breaks CFT as classical gravity does, but C is not proportional to m, to the mass of the produced sterile neutrinos. So, in total, there are no general arguments to naturally suppress C and is treated as a free parameter as long as C is smaller than 1 to have an EFT description. So, based on that, now we can move forward and to calculate the fermion production rate in this case. So, in this case, we have that phi square is parameterized in this relation here. The time-dependent part of the inflaton is parameterized in this relation here, where omega is the oscillation frequency and zn are slow functions of time. So now we calculate the amplitude of vacuum to produce these particles, and of course is proportional to the Wilson coefficient, and then we average over all the spin cases, and this will give us the decay rate, which is the sum over all the modes n that can be produced by the inflaton oscillation. And we end up with this relation here. So now, in this scenario, in contrast to the during inflation particle production, here, in order to calculate the number density, we need to solve the simplified Boltzmann equations. And we do that as a function of the scale factor here. So we need to know how the decay rate and the Hubble scale with A. For that, we have to choose an inflaton potential. We do two scenarios. One is quadratic inflation potential and the other is quartic. Here I will describe the quadratic, but I will also present the quartic result. So choosing the quadratic potential and parameterizing, of course, the time-dependent part of the inflaton like this, with this periodic function, we find gamma as a function of the scale factor, the Hubble as a function of the scale factor, and we put everything together, solving the number density Boltzmann equation, and we find the time-dependent number density here, and how it scales with the scale factor, and how it depends on the Wilson coefficient. A very important and crucial part is that we can interchange, we can actually introduce the Hubble parameter at the end of inflation and the Hubble parameter as a function of A, and we can interchange that with the energy density of the produced thermal plasma due to the inflaton oscillation. This will inherit to these equations the dilution factor delta NR, which is essentially the ratio of instant reheating over delay reheating, and this goes proportionally, and then we calculate the number density, the yield of this produced dark matter, and it is inversely proportional to this dilution factor. The bigger is the dilution factor, of course, sorry, the more the reheating is delayed, the bigger is the dilution factor, and the more the relic abundance is diluted. So now we can compare again our produced yield of the sterile neutrinos with the standard relic abundance, and we find out some upper bound under the standard high scale inflation on this Wilson coefficient. And we see that if the mass of the sterile neutrino is approximately or bigger than GeV, then we need a very fine-tuned, very small Wilson coefficient, unless the dilution factor is huge. Otherwise, we will make overabundance. We will essentially make the universe too dark. Now, for the quartic inflaton potential, we follow some similar procedure as before, with some associated parameterization of the parameters. But the important and crucial result is that the relic abundance calculated in this scenario is completely independent of this dilution factor. No matter how delayed is the reheating temperature, the relic abundance will be the same. This is a very crucial and very interesting result. And in both scenarios, quadratic and quartic cases, for mass of sterile neutrinos around keV and Wilson coefficient around 10 to minus 2 or 10 to minus 1, not much fine tuning, this quantum gravity dimension 5 operator with the small Wilson coefficient can generate all of the dark matter even in the KV regime. And this is very important, as I will show you momentarily. So sterile neutrinos are called dark matter in these cases, in contrast to the Donaldson-Withrow mechanism, because where the energy density of the sterile neutrinos is related to the standard model thermal bath, so the temperature of the standard model. In our case, the energy of sterile neutrinos is proportional to the mass of the inflaton, which is much smaller than the potential of the inflaton, the fourth, which is proportional to the thermal bath temperature. In other words, even for temperatures of standard model bath much bigger than the mass of the sterile neutrinos, in this case, the energy of the sterile neutrinos is already smaller than their mass, which means that they are already cold at the stage of structure formation. Again, a cold dark matter candidate. And now, to connect the first point with some observational constraints, we have the following. The gravitational production mechanism that I just described is operative irrespectively of the active sterile mixing angle theta, which means that this can easily give us some observational signals from dark matter, sterile neutrinos in this case, decaying to active neutrinos and photon, or to active neutrinos and E plus E minus. Which in turn gives us some X-ray and gamma ray emission, as well as some SIMB distortion as possible signatures of decaying dark matter via monochromatic photons. So we have strong observational predictions in this scenario. And to connect again all this discussion with what I said previously, now indeed we are in the top left corner. We can be easily, without any problem, on the top left corner of this diagram here, where for a relatively big mixing angle between sterile and active neutrinos, and with relatively small mass of these dark matter candidates, we can have still viable candidates which can be observed in the already or future experiments. So we have strong predicting signals. And with that, I would like to proceed with my conclusions, saying that in this work, I described dark matter in the form of sterile neutrinos produced only gravitationally via inflaton during and after inflation. During inflation, the relic density is proportional to the Dirac sterile neutrino mass, and even though it is enhanced due to this Higgs condensate, it's extremely suppressed, unless M is huge, the mass is huge. The post-inflationary scenario gives us some quantum gravity non-normalizable operators that indeed, for a small but not fine-tuned Wilson coefficient, can constitute all of the dark matter of the universe, even in the KV regime. And now, please stay tuned for our future plan, where we are going to study how standard model can be produced and reheat the universe during inflation due to this cosmological gravitational particle production via the Higgs condensate. And with that, I would like to thank you. Ευχαριστώ και σταματάω.